Hi everyone, this is Holly and Jess, and we are going to host a bit of a session on what is an anomaly and how do you detect it in data, with the aim of kind of helping from a data science perspective, getting a handle on geological data. So I'm going to talk from an annoying geologist point of view and ask questions that are probably really frustrating to a data scientist, and Jess will be able to translate that for you, hopefully in a really meaningful way.
Fingers crossed.
Okay, so what we thought we'd do is we'd focus on three specific types of anomalies which are really common to see in data. And I should have said this is related to the Explorer Challenge specifically. So the first one we're going to talk about is the physical characteristics of rocks. So in the Explorer Challenge you've got a lot of geophysical data. So why do we collect that? What are the characteristics in that data that we can look for? So as a geologist, what I'm looking for in that data is what can indicate to me a geophysical anomaly, a physical difference in something in the rock that's different from what's around it. So certain types of ore bodies, as an example, sulfide ore bodies, they're more dense and they're more conductive than the surrounding rocks. So I go and look in the data for signals that might indicate to me more dense or more conductive rocks. How I do that is I get someone to go and fly an airborne geophysical survey for me, probably magnetics, EM, gravity, and then I get someone much smarter than me to do some nice maths on it and invert that data and provide me back with a pretty image that has coloured with red as high magnetics and blue as low, and then I basically go and look for structures and trends in that data where it would indicate to me that something different is going on. I might be looking for a particular change in rock type and physical characteristic. I might be looking at a structure. I might be looking for chemical change, which is indicated by a difference in density. What else might I be looking for?
lots and lots of things. I guess I'd start by noting that you've kind of talked about 5 or 6 different steps with this data. So there's the raw data that you get off the instrument.
Yeah.
There's some processing of that data. So for example, if it was magnetic data, you want to remove the effect of the Earth's magnetic field, so that you're just looking at what the local geology is contributing to that field, for example. Then you mentioned inversion, and you also mentioned pretty maps, which I think are 2 separate things.
Yeah. So I guess the geologist's perception of what an inversion is kind of that, we're recording raw measurements from the Earth, which is kind of the physical characteristics are causing this signal to come back to us. But what we actually want to know is what it's telling us. And usually during the inversion process, we apply some prior knowledge if we have it. So ideally, if you were a very savvy exploration geo, before you went and did your survey, you'd have provided to your geophysicists some characteristics of the rock that you already know. So if you already know a bit about your geology, what rock types are where, a bit of their characteristics from, say, some samples that you've got, you can give those to the geophysicists, which allows, when they're doing their inversions, to provide you back with a better model that honours the samples and the geology that you already have to set.
Yeah, I think so. And so if you're coming at this from a data science perspective, essentially the thing that we don't do very well in exploration, which we should do better at, is understanding the background, as well as trying to understand the anomalies. So obviously, as geologists, we're looking for mineralisation. We want to find that big spike of sulfide that's going to make us all rich, and we don't spend enough time sometimes actually understanding what that background actually looks like and what the natural variability of the rock is, so that then we can threshold properly and say this thing is actually an anomaly. So one of the advantages that we think data science will be able to bring to this competition is potentially taking a larger look at some of the more public data sets and trying to understand what that natural variability is, so that then when you're presenting your anomalous target to Oz Minerals, you can say, well, actually, we looked at all of the greenstones in South Australia, and they have these kind of geophysical signals, and this thing is just sitting way outside that, so we think that's worth going and drilling. So being able to provide that kind of bigger data or higher level view, I think would make for a really good submission.
And so what I don't understand from a data science process is, from a geophysical data set, where if you look at your raw data, if we give raw data to data scientists without any of that context about the inversion, like how useful is that?
Well, I think there's still a lot of things that you can kind of pull out of that data without having to do a full inversion. So just to clarify some of the language, right? So when I would talk about an inversion coming from a physics background, I would expect that we have some governing equations that describe how the physical properties of the rock lead to the signals that we see in the field. And when I'm doing an inversion, I'm basically trying to go from the field back to those physical properties. And that works well when you're just looking at one or two fields, so like just looking at mag or just looking at grav. And in fact, there's a number of people out there now that will do mag and grav together, for example, into joint inversions. When it becomes really hard is when you're trying to actually stack a whole bunch of other data on top of that as well. So for example, we don't have any governing equations that tell us simultaneously how the rock's magnetic and density properties, plus the geochemistry, plus the mineralogy, plus the structure. And you put all of those things together, that system of equations is just too complicated to invert properly, which is where there's this big advantage for machine learning, is because potentially with machine learning we don't need to solve that inversion problem, but we can actually be looking for patterns in that. So we're really interested in this kind of data fusion approach as opposed to a more traditional inversion approach. That said, if you have expertise that can do that inversion for you, and you can start to constrain that inversion with some other data sets, then that's also a really valuable way to go, and that can actually then feed into a machine learning model as well. So again, lots of different ways that you can start to bake machine learning in. It's not a case of just take all the data and out pops some anomalies, but there's a lot of approaches that you can take without necessarily having to understand everything about how to invert a gravity field or how to invert magnetics or how to invert EM. So do we want to move on to geochemistry?
Yeah, I think we should. So geochemistry, that's my favourite topic. I'm much better at that than geophysics. So what is an anomaly when we talk about geochemistry? So I think the first thing to point out with geochemistry, when we collect data, when we talk about geochemistry, that is basically assay data or some real-time chemical reading or indicator of what the elements are within your rocks. So usually our geochemistry databases are either from drilling, and so you would find them either if you're drilling a resource, say a developing mine, there'll be lots of drill holes close together, or if you're doing regional targeting, you'll have drill holes where you might have data on a meter by meter basis, but there might not be another hole for 200, 500 meters. So I imagine it's really quite difficult from a data science point of view, given that sparse nature of the data. Having said that, what we look for in an anomaly in geochemistry is significant change that is indicative of potential mineralisation. So my process of going through geochemical data when I'm looking for anomalies is firstly to segment that data. So I know that if I look at the data in bulk, it won't necessarily show me meaningful trends. It's probably going to show me different rock types because that's probably what the bulk of the data is. But I need to separate those different rock types out, so separate that data into separate populations so that then I can see the actual anomalies stand out within those separate populations. So the first thing I do with a set of geochemistry is segment that out into different rock types, and even into potentially subset that again into different alteration types or different other subsets within that data, so I can really clearly see what are the anomalous points in there, because they can be from anything. So when we talk about chemistry, a lot of the time when it's a new deposit, we know we're looking for something different, but we don't know what that is. It could be an enrichment of something, but it could also be a depletion of something. So really we're just looking for something that stands out as different in a certain area. And
this is where there's a real opportunity to connect the geochemistry data that you've got directly to a geological process that's actually forming the deposit. So Holly hasn't mentioned it, but what a lot of geochemistry is about is trying to understand how different elements behave under each of those processes. So for example, you might have a bunch of hot fluid moving through some rock, and what that will do is that will change all of the minerals in that rock, and you will see some elements like things like silica, things like minerals like plagioclase and so on. They will be altered into clay minerals, or they'll lose the silica, and that will get transported and taken away somewhere. But when you can see that kind of alteration, that's an indication that there's been a hydrothermal process acting there, and so you might be thinking then about hydrothermal deposits like gold or some kind of copper thing around an intrusion or something like that.
So geologists, like as we kind of learn through our education, we develop a broad understanding chemically of what an unaltered and an altered rock looks like. You know, if we talk about, you know, breaking it really basically down to sedimentary rock, metamorphic rock, igneous rock, like a geologist will understand the different chemistries of those rocks in their natural state and potential elemental indicators that they've been altered. So we apply that knowledge when we're looking for evidence of economic mineralization and evidence that fluids have been through there. So we do apply that kind of knowledge that we've learned about those physical systems.
And one of the really exciting things I think about the data set that you've got for the Explorer competition is that there is such a broad range of elements. So each element behaves differently in each of these processes, but groups of elements behave similarly. So there's actually a lot of information that you can get about the kind of alteration processes that are happening by being able to compare groups of similar elements together. And geologists have a whole bunch of language around things like lithophile elements or hydrothermal elements, or you can go on Wikipedia and kind of search all of these things. But that will probably give you an idea of often what you can start to do is take ratios of elements, and it's actually the ratio of the elements that change that gives you this real big indication that things change. One other thing I'd touch on just as a technical point is that you don't want to be just using the raw elemental data out of the chemistry. The key thing about all of those assays is that all of the assay has to basically add to 1. I can't have more than 100% silica in a rock. So you need to basically be looking at using log ratio transforms or something similar to actually transform that data into a space where you could start to apply your traditional clustering methods. The geos at Oz Minerals mentioned IOGAS as a tool that geologists use to do a lot of this log ratio transforms. If you're doing this in a machine learning setting, you probably want to look at implementing this yourself. It's really straightforward to do. If you get stuck, ping me on the Slack and I can help you.
So that's geochemistry.
I think that's geochemistry.
Covered. I could go on for ages. Anyway. So the last one is structure, which I'm a terrible structural geologist, so probably, hopefully I can do it some justice. But what we're talking about in structure is we're talking about, features in the Earth's crust that may have been involved with mineralization. You know, we call them things like faults, like breccias, like different things that have happened which may have facilitated mineralization to occur. We might call them traps or sinks, or basically there's a reason why that this certain feature has allowed fluid to either flow along it or has made it easier or has created a barrier or a difference, a chemical gradient or something like that. So we look for those kind of features in the data, particularly around faults and I suppose intrusions of structure.
I mean, if you think about it, you're really looking for places in the Earth's crust where we can concentrate elements. And there's a few ways that we can concentrate elements. We can have sort of transport pathways. So we mentioned fluids before, that if you've got, you know, faults that are acting as preferential pathways for those fluids to pass through, then you're more likely to be then bringing all of those elements together on that, around that kind of fault plane. So that makes it a good target for trying to find that mineralization on top of it. And similarly, you're often looking for areas where things change. So if you imagine, for example, you start off with a fluid deep in the crust and you bring it up along a fault. If down deep in the crust, it's already sitting in chemical equilibrium with all the rocks around it. And as you bring it up along that fault, it comes into contact with other rocks, and there you can have chemical reactions. And as those chemical reactions occur, that will tend to then precipitate out certain elements, which hopefully are the things that you're looking for in your mineralization. So trying to look for places where we have these kind of guiding structures, these transport structures that are going to be bringing material from a broad area into a really narrow area. This is kind of this transport to trap mechanism. And then looking for the characteristics of that trap, the thing that's going to be different, that's going to make things precipitate out. Now, it's not always the case that for every deposit that you're looking for something on a fault. So you can have things like, SEDEX deposits, where you're looking at variations in groundwater that are actually causing things to precipitate out. But this is kind of generally what we're looking for, are these sort of areas where things change, because that's where you're going to have these traps occur.
Yeah, and structures, I suppose that if we think about how do we look for them in data, what is a structural anomaly in data, two things to kind of bear in mind. Often, just by their nature, ore bodies are fairly subvertical to vertical. So if you have potentially like a plane like this where your mineralisation is sitting, if you looked at it from above, it would look like a fairly linear, straight, thin line. So we look for those in the data sets, and that's often found in geophysics because there's often a contrast across that structure, either in density or conductivity or resistivity, which enables us to pick that up. We also do a lot of mapping, so structures and faults are something that, you know, a key that we pick up in mapping on the surface. Obviously, a lot of this project is undercover, so the geos haven't been able to do that, but that's certainly something we look for. Indicators in the rocks, not just for the structures themselves, but indicators quite close by that indicates that something's moved, that there's been a shear or a stress on that rock that's created a feature, or there's going to be a feature indicated there. And these things, it sounds kind of obvious, but they're not always obvious to see. And something that Ian brought up on the geology webinar, which is really key. Often the most obvious structures in your data set are not the ones where mineralisation occurs. It's often the second, third, or even fourth order structures that are the ones that are really of interest. I don't know why that is. Probably the major ones are just too easy for fluid to flow through.
Yeah, and you're looking for where things change.
Yeah.
The key thing about the depositional trap is it's not occurring everywhere. It's only occurring in a very specific location, so it's got to be different to everything else around it. I would say that if you're from a data science point of view, you're looking for changes in these faults, then you should be thinking about trying to do some kind of spatial filtering, particularly on the potential field data, so the magnetics and the gravity. Mainly because what you're looking for are high frequency changes. So you'll generally, when you look at, say, the magnetic map, you'll see broad features that are indicative of, you know, changes in cover thickness or changes in the bulk behavior of the rock, and then you'll see really fine scale blips and bumps, and those are, some of them are just noise, but some of them are actually these kind of really fine scale fault features, for example. The other thing that's available in the Explorer dataset is the South Australian government's just released their magnetotelluric data as well, which is...
Yeah, don't ask me much about that.
No, it's sort of deep crustal stuff. So if you're interested in trying to understand, you know, where deep fluids might be coming from the crust up into the Mount Woods area, then it's probably worth taking a look at those. I think they've got depth slices for the entire state. That's naturally at a very low resolution, but that might be helpful for you to try and start targeting things. So I just wanted to kind of tie this all back into, like, what should you be trying to do with your data science aspects. And I think the key thing about data science that we can do that the geologists can't at the moment is we can provide context for what is an anomaly. Yeah. So we've talked about, you know, whenever we've tried to define for each of these data sets what an anomaly is, we're kind of got all these caveats, you know, well, I know what a chemical anomaly looks like, but I know that it will look different in a granite than in a greenstone than in some kind of metasedimentary sequence. What we can do in data science is we can extract all of those as covariates to our predictor. And so we're essentially trying to say, given that we know that all of the background rocks look like this, tell me whether this is anomalous.
Yeah. And
that's really what you should be trying to do. So if you're trying to convince a geologist that your model is worth something, you're trying to say, this is the context that my model is adding to your interpretation of this data.
Yeah,
so definitely. You can get that conversation going. And that's why we think you're probably going to want to have both the data science aspect to go from lots and lots of data to just the context you care about, and then have that conversation with a geology expert to be able to then validate and say, well, we think this is anomalous because of all of these reasons. Does that actually link really well to the geological processes that we think are occurring, or the sorts of transport, trap, footprint models that geologists are well used to?
Yeah.
So you can bring that kind of prior information from the geologist into your model. Awesome. And that's what we're really looking for, I think, in a good submission.
Totally. So I think to kind of wrap that up, so we've just gone through and talked about what is an anomaly and how do you look for anomalies in the key data sets that we've given you for the Explorer Challenge. So I think to kind of actually step back out to some of the things that the geos were talking about in the webinar, just kind of flick back to why they haven't necessarily or previously described anomalies in the way that we're asking you to. When you are working as a geologist for a company, there are additional constraints applied onto you. So, you know, we don't just get told as geologists, go and find anything, go and look for anomalies. Usually, sometimes we do. But usually there's other things that are driving what we're doing. So particularly for the Oz Minerals geological team, they'd already found prominent hill. So really looking to use that model to find similar local extensions of that style of mineralisation. So very driven by a particular model, looking for particular styles of anomalies. So they may have missed some of the other types of anomalies in the data which do not indicate necessarily prom hill in the same way that they had indicated it.
And to be fair to them, that's kind of fair enough, because
Yeah,
if you've got prom hill with a whole bunch of processing equipment there, you don't want to find another type of deposit that's going to need a completely new plant. You'd rather find something similar, so you can just plug that into your existing investment.
Yeah, and that's totally how we work in the industry, in that most exploration companies, whether they be small or working for larger miners, we have a focus on a particular commodity, particular style of exploration. So it focuses us and allows us to apply our funds in a particular way. But it does mean that we might miss other things because we're really focused. Likewise, another, the constraint that the Oz Minerals guys talked about was that they had an operating mine, so they're always looking to extend the mine life as well and get more material to feed through that mill. So when the reasons why we haven't necessarily applied some of the techniques we're talking about is because often we're very focused. So we're encouraging you to not be focused and to look for other interesting anomalies in the data set.
Cool.
Thanks. And
Thanks
let
so
us
much.
know if you have any more questions.